In this video, I'm going to work through 34 questions that you may see in a first exam in a second semester organic chemistry course. And in the description, I'll have a list of all of the topics that we're going to discuss in this video, and I will have specific timestamps for each of the 34 questions with a very short description of the question type. So like, for example, we're going to start with question number 1 here, and this has to do with contributing resonance structures. So in the description, I'll have something like resonance structures for question number 1 with the timestamp, and I'll do that for all 34 questions. So check that out if any problems are particularly interesting for your studies. So with that, we'll get right into it. So number 1, like I mentioned, is draw the contributing resonance structures for the following molecule. So this is what we have here. This is an allylic position. This means that it is adjacent to a pi bond. In this case, it's a carbon-carbon double bond, and we have a conjugated system. Conjugated means that you have a pi, sigma, pi alternation pattern like this, where you double bond, single bond, double bond. So what this immediately suggests to me is that we're going to delocalize the pi bond towards the carbocation, because in these resonance structures, you're always trying to move the electrons around, and you need to start from a point that is electron rich to go to a point that is electron poor. So in this case, we have our alkene as our electron rich region, and that is going to move to the carbocation, which is electron poor. So our first structure here is something like this, where we move the alkene double bond towards the carbocation, creating a new carbon-carbon double bond, like this. And now you have to think about where that puts the carbocation, and well, we've moved the pi bond away from, let's call this carbon 1 and 2. So we moved the pair of electrons from carbon 2 because they're staying on carbon 1 in the new structure here, carbon 1 and 2. So 2 then has the carbocation because it is the position that is lacking the electrons that were originally there in the double bond. And then you could do a very similar thing with which was the conjugated double bond, which is now unconjugated or not conjugated because it's away from this alkene. But either way, you can start there as your electron-rich region, move that towards the electron-poor region, which is the carbocation, and create now the last structure here. And notice when I draw the final product here that the first and third are very similar because they have a conjugated it's a conjugated diene. It has 2 alkenes that are in conjugation. However, this is exocyclic, meaning that the pi bond is outside of the ring. It's attached to the ring, but it's going away instead of these endocyclic pi bonds here. So if you had to rank these in terms of contribution, this is probably the most stable because of the conjugation and the endocyclic nature. And then this is second because, again, the conjugation and the exocyclic makes it slightly less stable, and then here there's no conjugation. So you may wonder, well, this is a primary carbocation. It's not really primary because it's allylic, so that makes it a little bit different, and this conjugation is going to be predominating here. But really, this question was just asking to draw all 3, so here are the structures, and that is all you need to know for this one. So we'll move on to question number 2. So question number 2 is, which of the following resonance structures is more stable and why? So this is kind of getting to the point that I was just talking about with the previous question about ranking those stability. But here we have these 2 specific structures. So here we have a carbocation initially, and then we use the lone pair of from the oxygen to move that down to form a carbonyl, which then the oxygen takes the positive charge. Now, this was very difficult for me when I first learned about this because if you think about this in terms of electronegativity, you're going to get the wrong answer. Because like in general chemistry, or even in an organic chemistry class, one of the first things that you're introduced to is electronegativity, and you're saying that you want the negative charge to be on the more electronegative atom, if possible. And that's true. So the corollary would be the positive charge should be on the less electronegative atom or the more electropositive atom. So if you take that point of view, this structure has the oxygen with a positive charge. That's more electronegative than carbon. So here, the carbon has a positive charge. That's the more electropositive position. So you would expect on that basis that the carbocation here would be more stable. And there is some argument to be made for that, but we're forgetting about the most fundamental rule that we learn in any general chemistry class, and it's that atoms prefer or are most stable if they have an octet of electrons. So this is the only way that we can explain this question. So let's analyze the atoms and see which has octets and if there's a structure that has octets and one that does not. So if we look at the carbocation, our oxygen does have an octet, even though it's not drawn in the actual resonance structure. Only the one lone pair was shown just because that was what was involved in the resonance structure, but there's two there because we know that because there's no charge on the OH. If you're confused with formal charge, I have a video on that. I'll have the link in the description as well for you to check that out if that was confusing. But either way, you have a full octet of that oxygen. The hydrogen, we know that only needs one pair of electrons, only two. That is one of the exceptions. It has a single bond to the oxygen, so it's satisfied. But now this carbon with the carbocation with the positive charge does not have an octet. It only has 3 single bonds. There's no hydrogen at that position. That's like, it's not a hidden or understood hydrogen, because if it were there would be no positive charge on the carbon, which would mean there would be no carbocation. So you have to not have that fourth set of electrons to have this charge to begin with. So that carbon only has a sextet. It only has 6 electrons around it in the form of those 3 bonds. So that is the reason now, because if we move to this structure, we'll see that that same carbon now has an octet. It has the 2 single bonds and then a pi bond and a sigma bond in this double bond to the oxygen. So the total electron count is 8 electrons at that position. So, and then the oxygen as well still has an octet, even though it has the positive charge. It's got 6 electrons in the bonds, 4 of them to the carbon here and 1 to the hydrogen for a total of 6, and then the single lone pair, again, giving the positive charge, again, because of formal charge counting. Again, the video in the description will help with that if you're confused there. But the point is, all atoms have an octet in this structure. So this is, in fact, the more stable resonance structure and the higher contributing form, because we have an octet in all atoms, whereas in the first structure we do not. All right, we're moving on to the next question here. So the next question has to do with ranking dienes towards their reactivity towards Diels-Alder cycloaddition. So remember, Diels-Alder cycloaddition is a pericyclic 4+2 cycloaddition. Again, if you're confused on what those terms mean, I'll link the video I did on the Diels-Alder in the description as well. But what we are asked to do is rank the dienes in decreasing order of reactivity. So that means the most reactive is first, and we go down in a decreasing order like that. So remember that dienes, the key here is that dienes in Diels-Alder are more reactive if they have more electron donating groups. So dienes are more reactive with electron donating groups. So I'm going to call ED groups. Okay, so now we have to look at our structures and see which ones have electron donating and which one has electron withdrawing, if that is the case. So the opposite is true. If dienes have electron withdrawing groups, they are less reactive towards Diels-Alder cycloaddition. So here we have dimethyl. 2 methyl groups are a substituent on our diene. So we know that methyl groups are slightly electron donating through hyperconjugation. So we'll just call this molecule 1, 2, 3, and 4. So if we just look at 1, we're like, okay, that is slightly activated towards Diels-Alder cycloaddition because it has somewhat of electron donating groups. If we look at molecule 2, this has cyano groups. Cyanos are extremely electron withdrawing because there is a carbon-nitrogen triple bond, which makes that carbon extremely electron poor. So it's in essence sucking the electrons away from the alkenes to stabilize that partial positive charge. Because remember, electrons they're not really localized as we show them in these structures. They can freely move, and what I mean by that is the electron density can be more dense at certain atoms in the molecule depending on what's going on. So in this case, we have a very electron poor carbon. So to stabilize that, we have some of the electron density is moving towards the carbon, withdrawing it away from the alkene to stabilize that in essence. So a very electron withdrawing. So this would be a terrible diene for a typical Diels-Alder. Then if we look at molecule 3, we have a lone pair on the oxygens, and that can donate towards resonance. So because of the donation of the resonance effect, this is extremely electron donating, even though oxygens are, by induction, are very electron withdrawing because of their electronegativity. But if you can have this resonance effect with a direct lone pair, that like wins in essence. That is a more significant factor, which makes this extremely electron donating, these methoxy groups. So, all right, and then if we move to molecule 4, those just has hydrogens, so that is our base. So now if we summarize what we just talked about, 3 is extremely reactive towards towards cycloaddition. So I'll just call this molecule 3 is the most reactive, so that is less than 1. We know 1 is more reactive than just number 4 here because we have the methyl groups which slightly activate it compared to just the hydrogens. So, and then 4 is next because that is at least not deactivated like the dicyano molecule is. So this would be the final order for this diene reactivity. All right, and then we'll move to our last question. This is again another Diels-Alder, but it is now looking at the dienophile. So the rule for the dienophile, the empirical rule that was seen by experiment, by observation, is that the dienophiles are more reactive if they're electron poor. So dienophiles are more reactive with electron withdrawing groups. So EW groups, we'll call them, like the cyano group that we saw in the previous question. Here we have aldehydes and methyl groups are our 2 substituents that we're comparing. So again, I'll just label these something so we can refer to them even more easily. So molecule 1 to 4, going left to right. So molecule 1 has 2 carbonyls, 2 aldehydes. Again, those are extremely electron withdrawing because it's very similar to the cyano group. We have these dipoles here, which makes the carbons extremely partial positive right next to the alkene, again, kind of sucking some of those electrons away from the alkene, which makes them electron withdrawing substituents. So 1 would be extremely reactive towards Diels-Alder because it has these strong electron withdrawing groups. And now by the way, we're going in the opposite order this time. So the least reactive to the most reactive. All right, so if we look at molecule 2, we have the aldehyde again. That is very electron withdrawing, so that will increase the reactivity. And then we have a methyl group. And as we just looked at in the previous question, methyl groups are electron donating through hyperconjugation. So that would actually deactivate the dienophile towards cycloaddition. So this has a really electron withdrawing group, slightly electron donating group. So this is somewhat activated towards Diels-Alder cycloaddition, but not extremely. And then if we look at 3, this has only the aldehyde. So this is going to be more activated towards Diels-Alder cycloaddition than molecule 2 because we don't have the hindrance of the methyl group. Remember, we want the most electron withdrawing groups as possible on the dienophile to make it the most successful Diels-Alder. And then if we look at number 4, this has just a methyl group. So this is actually deactivated towards cycloaddition. So we want to go in order of increasing, reactivity. So the least reactive is molecule 4. And then next is molecule 2. We know that 2 is less reactive than 3 because of the presence of the methyl group. So 3 is next. And then the most reactive is 1, which has the dialdehyde, right? Which, again, both of the aldehyde groups activate the dienophile. So you ultimately get the most reactive species. All right, here we have our next set of questions. So here we are asked to determine if these molecules are aromatic, anti-aromatic, or non-aromatic. So again, let's recall the rules for aromaticity. So first of all, the molecule must be cyclic. These are all cyclic, so that's an easy one. 2, they must be fully planar. In most cases, this just means that all carbons are going to be sp2 hybridized, but occasionally planarity is referring to the three-dimensionality of the molecule. So sometimes the nature of the molecule is going to force it into a planar or not planar shape, even if you have all sp2 centers. But in general, this is good enough, is that you have to have sp2 centers to have planarity. Right, and then 3, you need to have fully conjugated. So again, this means that you need to have a pi, sigma, pi alternation at double bond, single bond, double bond, all the way through your cyclic ring. And then lastly, it has to follow Huckel theory, which needs to have 4n plus 2 pi electrons, where n is 0, 1, 2, so on. It's 0 or an integer, a positive integer. So this means that you can either have 2 pi electrons, 6 pi electrons, 10, and so on to get to your Huckel theory number. And this is for aromatic. Now, anti-aromatic follows the exact same rules. So let's just say for A, right? Now for B would be anti-aromatic, and this follows for N pi electrons. Again, where N is 0 or a positive integer. You can't really have, for the anti-aromaticity, it needs to be 1, because if you had 0 pi electrons, you're not going to have anti-aromaticity either. So N for this case does have to start at 1, and then so on. So positive integer. All right, so let's go through these systematically then. If we look at A, I'm going to redraw the molecule here since it took up a lot of the space. So let's start with our rules, right? Is it cyclic? Yes. Is it fully planar? No. The reason we know that is if we go through all of these positions, the alkenes are sp2. They have 3 bonding groups at each position. But this carbon here is sp3. It has all sigma bonds, 4 bonding groups. That's sp3. That breaks the planarity. So A is neither aromatic nor anti-aromatic, so it's simply non-aromatic. Non-aromatic is our term for it just doesn't fit in anything else, so it's just nothing. It's just a cyclic structure, non-aromatic. All right, let's look at B now. Is B cyclic? Yes, it's cyclic. Is it fully planar? Well, let's see. All the carbons are. Certainly, they have the hydrogens that makes them have 3 bonding groups. Now let's look at the nitrogen. The nitrogen has that lone pair, which is the last bonding group, so it is sp2 hybridized as well. So that is planar. Now, how do we count is it fully conjugated, by the way? Double bond, single bond, double bond, single bond, double bond. It is. So it meets that rule as well. Rule number 3 here. Now, does it follow Huckel theory? Well, let's count our pi electrons. There is 6 pi electrons, counting the 3 bonds. But the question is, do we count the lone pair and the nitrogen or not? Well, if the nitrogen were to resonate in, so like this, I'll draw the arrows, but not the following structure, that is going to break the conjugation. So that's not a favorable thing. Also, it's going to make the nitrogen positively charged, and it's going to force it into this linear geometry because it's going to have this like alene-like a geometry where you have a carbon double bound to the nitrogen, double bound to another carbon. So this is not going to happen. So you don't count those lone pairs, the one on the nitrogen. So this is simply 6 pi electrons. That is a 4n plus 2 number. It's a Huckel theory number. It has, where n is 1, we have 6 pi electrons. So this is aromatic. Now C is different because we have to go through the rules again. It's cyclic. Is it fully planar? It appears not to be. But this is a tricky one. If we look at all the carbons, they're sp2 because they have 3 bonding groups. If we look at the nitrogen, the lone pair on the nitrogen makes it such that it has 4 bonding groups, and you would expect it to be sp3 and you would move on, and you would say it's not planar. And that would be correct. But remember, the lone pair can resonate. So just like we showed here, it could do this, but there's no driving force for it to do it in this case. But if it does it here, there is a driving force, right? Because if we do this now, right? So let's draw this structure. So again, by the way, this is a resonance structure, so you should draw the double-headed arrow, not equilibrium arrows. All right, this is going to give us this structure now, and then the negative charge on this. So there's a lone pair here on that carbon. So now that nitrogen has become sp2. And again, since resonance structures they're not isolatable structures, these molecules are constantly interconverting between these multiple options, these different structures. So if you can have planarity and full conjugation in certain structures, then the sum of them all is that it is fully planar and it's fully conjugated. Because again, we have one more structure that I'm just going to draw the arrows for, right? And then we can go back to where we started. So if you sum those up, like a superposition of all three, you're going to get a fully planar, fully conjugated structure that also has 6 pi electrons, because you have to count the lone pair on the nitrogen, because sometimes it is a pi bond that is contributing in the conjugation and planarity of the molecule. So therefore, this is a aromatic molecule. Okay, now let's move to D. D is cyclic, fully planar. Again, these alkenes have 3 bonding groups. I'm only showing 1 there. It's fully conjugated because pi, sigma pi, so on, all the way through. But now it has 8 pi electrons, no lone pairs or anything that we have to consider about that. But that's not a Huckel theory number. That's an anti-aromaticity number, where N is 2. So this is anti-aromatic, and that is it. Okay. Moving on to our next question here. So here we are asked to rank the following molecules in order of increasing acid strength. So in other words, that is in order of decreasing pKa. All right, now notice these are all phenols, which be careful with this. This is the alcohol, the benzene alcohol. And the name is just phenol, which is very different than phenyl, by the way. So let me take this time to show this. Phenyl is just a benzene substituent. Phenol is the alcohol benzene, right? The alcohol substituent on a benzene. So these are all pretty acidic because this conjugate base can resonate in to the ring. So I'll show one example. Right, so if we were to think about the resonance of this conjugate base, we can move one of the lone pairs that makes the negative charge here into the ring, and then we can move it all the way about. We can delocalize it all the way around, which makes the pKa of the phenol pretty low. The pKa is about 10. And if you think about the pKa of just a standard alcohol, it is like 15 or 16. So again, pKa log scales, right? So the difference between 10 and 15 is 10 to the 5th, right? That is a lot more acidic, right? If you have a pKa of 10 versus pKa of 15. All right, so they're all pretty acidic based on that. Now the question is, how do these substituents affect that pKa? Well, this example here, and you have an electron donating group. The electron donating group will donate its electrons towards the entire molecule, but the proton of interest is here. So it will make it such that there are more electrons in that bond. It's a very small effect, but through reduction, there'll be more electrons in that bond, which makes it less likely to be removed. So this actually stabilizes the acid and makes it less reactive. So a worse acid when you have electron donating groups. When you have electron withdrawing groups, that effect through induction is exactly the opposite. The induction of this nitro group will remove the electrons from that proton even more and make it even more likely to be removed. There's also a resonance effect going on with the orthonitro if you consider the conjugate base. So if we look at the conjugate base of nitrobenzene, or nitrophenol, I should say, we have this structure, right? So now, if you delocalize like a standard, standard phenol, you would get this structure here with the negative charge on that carbon there. Okay, but now that negative charge can delocalize to form a carbon-nitrogen double bond, and then the lone pair, or excuse me, the double bond can delocalize up like this to form another negative charge on this oxygen, which is favorable for two reasons. Well, one, it's just a whole nother resonance structure that none of the other molecules can have. And two, it puts the negative charge on the more electronegative atom, which, as we mentioned initially with the resonance structure stuff, this is more favorable if you can have it and you have no other like hindrances like we do with the octet rule here. All the atoms have an octet in both of these structures, so then you kind of like move down to in priority to these electronegativity effects, which end up being favored here, which would make this a extremely stable species. So the sum of all of that, or the main takeaway, is this ortho-nitro group has an additional resonance structure which makes this acid even more acidic. Now, the meta position does not have that same effect, right? Because if we move the negative charge to this carbon, right? Let me do this. I'll number all these carbons. Right. So if we have this negative charge on this oxygen, it will delocalize to carbon 2, to carbon 4, and to carbon 6. And you can prove this to yourself doing the exact same steps that we just did with the previous example. But if you notice, if the negative charge is on carbon 2, 4, or 6, it cannot resonate to the nitrogen because it's not on carbon 5. The negative charge isn't. So that would make there would be no additional resonance structure for that structure. So that makes the meta nitro, or the 3-nitrophenol, is less acidic than the ortho. Right, so now let's put this all together. I'll call this again molecule 1, 2, 3, and 4 going left to right. Right, so we are asked in increasing order of acid strength. So our worst acid was molecule 2 because we have the electron donating effects of the methyl groups. Then molecule 1, because we don't have the donating effects of the methyl groups there. And then 4, because we do have electron withdrawing induction of the nitro group, which is still better than just hydrogens, more activating of the acid strength. And then lastly, 3, we have that entire additional resonance structure and stronger induction because it's closer to the hydrogen. So for both reasons, we ultimately lead to this order. All right, and then lastly, in regards to this stuff, we have ranking the following molecules in order of decreasing base strength. All right, so now these last two questions are connecting the idea of acid strength and base strength. So the more reactive a acid, the more stable the conjugate base is. Right, so notice these are all the exact same questions that we just had. The order is slightly different, and they're the conjugate base. But we did just determine that the conjugate acid to this is the strongest acid. So that means that that molecule, let's again order this left to right, the molecule 2 is the strongest base, or the most stable base, I should say. If we're talking about base strength acting as a base, then this is actually the least reactive base because it's the most stable. It's the most likely to be content and have lowest energy, so it's not going to react in any way. But if you were to consider like the methyl group on the benzene, on the phenol, this is now the very strong base because this was a weak acid or weaker acid. So what that means is the acid is more stable than we would have the other options, which means its base is more unstable and more reactive. So basically, the takeaway here is acid and base have this relationship that a strong acid equals weak conjugate base, right? And the opposite is true. So a strong base equals weak conjugate acid. So here we know what we just determined in the last question was the conjugate acid to 2 is a really strong acid. So that means that this base is really weak and stable and not reactive, right? So similarly, that means that 4 is extremely reactive base because its conjugate acid is very weak. So let's put that in order then. So we were asked to go decreasing base strength. So the strongest base is 4, then 1, then 3, and then 2. Again, this is the opposite of the order that we just looked at, where we're now looking at the base strength. So this has the induction effect of the methyl group, which makes this extremely, well, not extremely, but less stable. Then if we look at 1, this has just the protons, the hydrogens on the benzene, which has no net effects really. It's just like our baseline. And then we have the meta-nitro group, which stabilizes everything by an induction. And then here we have the further stabilization because of the extra resonance structure. So this is really just the connection between acid strength and conjugate base strength. All right, here we are asked to rank the following in order of increasing reactivity towards electrophilic aromatic substitution. All right, so our typical rules for electrophilic aromatic substitution is that electron donating groups will activate the ring. So electron donating groups equals more reactive. Right? And the reason for that is they stabilize the intermediate, which is the carbocation that breaks the aromaticity. If you have electron donating groups, you can stabilize that carbocation, which will increase the reactivity towards that type of reaction. So again, let's number these molecules left to right, 1 through 4. So if we look at 1, we have 2 methyl groups. Those are electron donating through hyperconjugation. If we look at 2, we have this COOH, which is a carboxylic acid, this type of structure, right? So we know that this is extremely electron withdrawing for the similar reasons that we were talking about with dienes and dienophiles. We have this dipole, which makes a partial positive on the carbon, which then kind of sucks the electrons away from the benzene. And then again, we have the methyl group, which is electron donating relative to the hydrogen. So if we look at molecule 3, we have 2 carboxylic acids, so those are extremely electron withdrawing and ring deactivating. Then if we look at 4, we have a methyl group again, which is activating, but now we have the special case of the halogens. So halogens are inductively electron withdrawing. So I'm going to say let me say IND for inductively electron withdrawing, because the halogens are super electronegative. They're among the most, they are the most electronegative group on the periodic table, so they are special in that case that their induction effect is very strong. However, they also have lone pairs on the carbons that are adjacent to the alkenes in the benzene, so they can be electron donating through resonance. Right, so the question is which one wins? Well, in terms of reactivity, the induction wins. The induction is a stronger effect and makes these deactivated slightly. This is slightly deactivated, whereas the carbonyl, or like a nitro group, is extremely deactivating through induction. But here, the counter effect of the resonance makes it such that this is slightly deactivated. Also, in future questions, we'll see that the electron donating effect through resonance actually makes this orthopara directing. The halogens are the only case that they're ring deactivating and orthopara directing. And again, it's because of the special nature of the halogens in terms of their electronegativity. So anyway, that is a nice overview for that. The chlorine is slightly deactivating. So then the takeaway then is if you look at molecule 4 to 2, the only difference is the carbonyl versus the chlorine. The chlorine will be less deactivating than the carbonyl, so 4 is more reactive in general. All right, so let's rank this order. We need to go in increasing reactivity. Well, 3 is certainly the least reactive because it's 2 extremely withdrawing groups. then it is now 2 is more reactive because, again, the halogen is less deactivating than the carbonyl. So that's why we get this order of 2 and 4. And then the most reactive is certainly 1, which has the dimethyl groups, which are both electron donating through hyperconjugation, which is an inductive effect. All right, let's move on. This is the same question with different molecules. We're asked to rank the following order in order of decreasing reactivity towards electrophilic aromatic substitution. Again, electron donating groups make them more reactive. So here we have a nitro group. Remember, the structure of a nitro group is this. So again, extremely deactivating because we have a full formal positive charge on the nitrogen. Okay, again, let's call these 1, 2, 3, and 4. So 1 is the most deactivated because the dinitro groups. If we look at 2, again, we have electron withdrawing through electronegativity, but not as much as the halogens because oxygen in general is less electronegative than the halogens. So what wins in this case is the resonance effect for both the directing and the activation. So this is extremely activated because of the lone pair. So this is actually going to be the most reactive out of our list. If we look at 3, that's dimethyl group. That's going to be less reactive than the oxygen. The oxygen, again, has this resonance effect. So electron donating through resonance, which is far more critical than the induction of hyperconjugation. So that would be the most, then the methyl group. And then here we have a nitro and the methyl group. So this is just more reactive than the dinitro, but again, it's less than both 2 and 3 because those are both donating groups on both of them. So if we need to go in order of decreasing reactivity, the most reactive is 2, because of the methoxy group, then 3, then 4, and then, oops, my this is actually opposite. The order was right, but my sign was wrong, right? So ignore this. All right, so 2 is the most reactive, so greater than 3 is the next reactive, which is greater than 4, which is next, and then 1 is the least reactive. So we are asked to go in order of decreasing reactivity. So yeah, this is the correct order. Okay, so be very careful of the type of order that they're asking for because you can understand what's going on and then just miss that small detail and get the whole question wrong, especially if it's multiple choice. So just take your time. All right, here we have our next question. So which direction does the equilibrium lie and why? So this has to do with keto-enol tautomerization. So this is an enol and this is a ketone. By the way, this is an enol because it has an alkene, so the En, and then ol because it's an alcohol, so hence the enol. And in general, a carbon-carbon double bond is weaker than a carbon-oxygen double bond because of the difference in electronegativity. So we result in a dipole, strong dipole here. Again, that's generally preferred for a stronger bond. So in a general sense, the equilibrium is going to lie towards the ketone. So in this case, to the right. So yeah, in this case, it's this direction. So let's just draw a larger arrow here and a smaller arrow that way. Again, because the carbon-oxygen bond is more stable in general. Now, there are certain instances that the enol will predominate, and we'll get into a specific question like that. But the general sense is if there's nothing weird going on, like there's no aromaticity gained in one or the other case, then you're going to lie towards the keto form all of the time, unless there is that weird like aromaticity or some other driving force. All right, so now let's move on to the next question, which has one of these weird cases. So here, which direction does the following equilibrium lie and why? So again, this is an enol and a ketone, so keto form. But this is phenol specifically. And we know that this is a benzene moiety, so this is aromatic. This is not, because now one of the pi bonds is no longer in full well, it's in full conjugation, but you've broken the planarity of the benzene, and it's exocyclic, which is in general less stable than endocyclic double bonds. So for both of those reasons, this equilibrium lies heavily to the left, because we have gained aromaticity in the enol form. So you have to kind of keep your head on a swivel with these types of questions. Sometimes the standard rule or the empirical rule that like the keto form is always going to predominate, it's not always, and that's why as chemists we don't like to use terms like that, because it's more often than not the ketone will predominate. But here's an example that we have the enol predominating, and it's due to aromaticity. So always keep an eye out for aromaticity, because it's the most stabilizing factor of everything that we've looked at so far. So that's the answer to this question, why it lies to the left, is aromaticity. All right, here we have the next question. So we're asked, would the following conversion be successful, and then why or why not? So here what we have is a Grignard. And remember, Grignards are essentially carbanion producers. So you can think of this as essentially contributing this methyl carbanion, which is going to be our nucleophile, this Grignard nucleophile. So what we're showing here in this conversion is that the Grignard selectively attacks this position and then creates this bond. So this methyl group, let's call it 1, is this carbon here. All right, now that's reasonable that the Grignard could attack in this SN2-like fashion, but this is not going to be successful, and the reason is the Grignard isn't going to selectively attack this position. It could easily attack the carbonyl as well, because the carbonyl has this partial positive and partial negative through the dipole of the oxygen, that the Grignard would attack that position as well. And it wouldn't selectively attack the Grignard, the alkyl halide, I should say. So this would be completely unsuccessful. And your major product after acid workup would be this, where you're still creating the new carbon-carbon bond that you wanted, but you're also creating this, and now you're at an alcohol. And now it's difficult to convert this back to a ketone. But as far as I know, it's impossible to do it directly. There are ways you could work around and do it. But this proposed synthesis can easily be done with just one step. So this is our with one correction step, I should say, not one step entirely. But what this next question is, propose a modification of the synthesis that would actually make the desired ketone in good yield. All right, so what we just saw, the problem is that we need this ketone to kind of go away so we can put it back on later. So, and if you remember, acetal and ketal formations are a way to protect the carbonyl, where they are not reactive towards Grignard nucleophiles, the acetal or ketal. So all you have to do to add to this is a protection and deprotection step, where you use some acid catalyst. I'm just going to say H+, but it could be HCl, H2SO4, whatever your favorite acid catalyst is. It needs to be relatively dilute. So, and then this is going to create the acetal, like this. Now you may wonder, does this attack the alkyl halide? And it might in some amount, but remember the acid catalyst, the point of that, part of the point is to protonate this carbonyl, which makes this carbon extremely electrophilic. So by and large, this will be your major product. Then you could subject this to your Grignard. I'm just going to put CH3- because we already saw the whole Grignard up there. This will now selectively attack the alkyl halide, because that's all that there is in the reaction mixture. And then you can easily deprotect this with, again, some more acid. This actually works with base as well, but here we'll just keep it simple with acid. That will get rid of the ketone, or get rid of the acetal. Well, excuse me, in this case it's a ketal. It'll get rid of the protecting group to get you back to the ketone, which was the molecule that we wanted in the original synthesis. All right. So now we're going to move to a set of predict the product questions, and this is kind of a hodgepodge of all of the questions that we looked at in the series of chapters. So there's going to be no particular order. It's just reactions of various types, and we're going to have to dissect them all. All right, so here, question number 13. we have a ketone. Again, we know that these are good electrophiles because of the carbonyl dipole. And then here we have an organolithium. Organolithiums are similar to Grignards in the sense that they provide a carbon nucleophile. It also can be a carbon base, but here it's going to function as a nucleophile because if it were to function as a base at these alpha carbons, there's not much that it can do besides reacting with itself in an aldol type reaction, which is possible, but here we're going to focus primarily on the nucleophilic addition. Again, these organolithiums are more likely to be nucleophiles as additionally, so that is why we are going to get this this product here. So notice what's happened. We created a bond between carbon 1 and 2. So I'm going to call the phenyl group 1 and the carbonyl 2. Right, the methyl group has stayed put on carbon 2. The carbonyl oxygen has become an OH because of our acid workup step in step 2, and the T-butyl group has remained unchanged. So mechanistically, I'll draw the first step here. It's really only one step because the acid workup is pretty self-explanatory, but this step will give you this. And then you just react to that base with an acid, and you'll get to this product here. Right? So that's our first product. Now let's move on to question number 2. Here we have a ketone and an alcohol and acid catalyst. So this is a Ketal formation, very similar to what we looked at in question B. And now the mechanism here is a little bit more complicated, but effectively we're getting rid of this oxygen, carbonyl oxygen, with 2 equivalents of the alcohol. So you end up with this. Now you may wonder, well, how do you know that you have 2 molecules of the alcohol? Well, keep in mind, there's always Avogadro's number or some amount, even if you're working on millimolar concentrations, there's a ton of molecules floating around, millions and billions, trillions, even higher magnitudes of molecules. So you can always have 2 of them react in one particular mechanism. That's never out of the question of possibility. So that's what happens here. And the reason is the Ketal formation is much more stabilized than the hemi-Ketal, which can easily break down. So the Ketal here, the alkoxide group, is actually isolatable and somewhat stabilized. So the mechanism for this, first you protonate the carbonyl, which I'm just going to show it as protonated, then the alcohol, so I'm going to call that OR, can attack now this good electrophile. This will make OH. This is now your hemiacetal. So there's a hydrogen still on the oxygen, and then the R group, and then your other R group, which was your starting. Then there's a proton transfer step, which I'm not really drawing the arrows for, just because it can be mediated by the solvent. You can draw it intramolecularly. There's just a lot of ways to show that. But now this step is very important, and I've stressed this a couple times before. You're going to have this oxygen kick out the water in a concerted mechanism. Because like we pointed out in our resonance question, this intermediate conserves all atoms have an octet. If you were to just have the water leave on its own, you're going to form a carbocation first, which has a sextet, which is less stable. So if you can kick out the water, the good leaving group, in this concerted mechanism, it's far more likely to occur. And that's what happens here. Then your second equivalent of your alcohol can attack now because you just created a really good electrophile once again. So then you get to this point, and now you have a proton transfer to get to the product, which I'm not drawing here, but your solvent or whatever can remove that, and you'll get to the product. And now notice R's are the ethyl groups here because we have ethanol as our alcohol, but I showed it in a general sense. You could do it with any alcohol. All right, and our last question of this set is is here, number 15. So this very first step is a Friedel-Crafts alkylation, and this is a tricky question because the actual intermediate that'll first form is this. So that's your first electrophile towards electrophilic aromatic substitution, which is this reaction scheme. Now, notice what type of carbocation that is. It's primary. That's extremely, extremely unstable. So this will quickly undergo a hydride shift to form this secondary carbocation, which is now the electrophile towards the benzene, because this step happens so quickly that the benzene cannot react with the primary. So this first intermediate here, the first product, I should say, it's not an intermediate, is this, right? This isopropyl group. Even though we started with just the normal propyl, we undergo this hydride shift to give us this secondary carbocation, which forms this product. All right, then we react this. This is an NO2 formation. If you're confused on how, like mechanistically how this works, I'm not going to show it here because it's time consuming, and I have another video illustrating how you form the nitro group for this type of electrophilic aromatic substitution. So again, I'll have the link in the description for that. But what this does, this is a ortho-para director, the alkyl group is, because it is electron donating, again through induction. So we'll get two products, the ortho and para positions. So the nitro group at ortho and the nitro group at para. By the way, you'll notice I put a circle here for this benzene. That's shorthand, again, because it has all this resonance, that it's really like there's like 1.5 bond character at each carbon. It's not really that you have these isolated double and single bonds. All right, here we have toluene, which is this methylbenzene, and NBS. So this is one of those cases that you're basically going to have to memorize what's going on here. So NBS is N-bromosuccinimide. Right, that might be spelled wrong, but it doesn't matter. It's N-bromosuccinimide, which is this structure. There's a nitrogen and then the bromine. And what this provides effectively is a bromine radical. And a bromine radical can add benzylically or allylically to a species, whatever you have. So here we have a benzylic position, which is this one here. I'll call it A. So the bromine is going to add to that position, and that's it. That's the product. This would be racemic if it was chiral. It's not, because these there's two hydrogens there, so there's no chirality. That's just the answer. So the point is, the mechanism is rather complicated and probably not expected in an undergraduate organic class, but we can go through it. I'll save that for a different video because it's a little bit more involved. But what you need to know is it's a benzylic brominator, which is a very useful thing. It's benzylic and allylic brominator, which can create good leaving groups for SN2 and other types of reactions. So very important that you can add your bromine there in the benzylic position. All right, let's move to the next reaction. So here we have a lot of alkenes, it appears. Like we have a lot of pi bonds, carbon-carbon pi bond. So this is difficult to recognize, but this is an intramolecular Diels-Alder. And what makes this a little bit easier to figure out is, first of all, it's done at reflux. And we know that Diels-Alders are typically difficult reactions to perform. So you need a lot of temperature. You need a lot of energy in the system to help it along. So reflux will aid in that. The next thing to notice is we have a diene here, intramolecular diene, and a dienophile here. So the combination of all of these factors is that we have high temperature, we have a diene and a dienophile in the same molecule. That's all very good indication that this is an intramolecular Diels-Alder. All right, so now how do you begin with actually doing this question? Well, I always draw the diene like we see in a typical Diels-Alder, like this, right? Where I'm just keeping track of the carbons. So 1, 2, 3, and 4, where 2 and 3 have these methyl groups, which is why I drew them here in this structure. Now we need our dienophile like this. Well, our dienophile is all the way out here, right, which is at carbons 8 and 9, right? So I'm going to put 9 and 8 like this. So now we have to connect 4 and 8, which has 3 carbons in the middle, right? So this is carbon 5, 6, and 7. And I drew it in this shape because I have a little bit of foresight on where we're going. But you could have just connected them any way you want, and it doesn't really matter. It's just going to look kind of messed up the first time you do it, but you can still work to the answer. So regardless of these intermediates, these connections here, I should say, this is still the reaction, right? So here's our dienophile. We're creating our cyclohexene, right? So this is carbon 1, 2, 3, 4, and we created a bond between 4 and 8. So here's 8, and then 9 and 1. So there's 9. And then 4 to 8 remains unchanged. So carbon 4 is bound to 5, which is bound to 6, which is bound to 7. Right, now I drew my line through carbon 8, but hopefully that's still clear enough. Here we have 5, 6, 7, and then 8 is that position there. Right, and then don't forget, you have your methyl groups at 2 and 3. Right? So now, if you were to draw this structure, kind of nice, in a way that you would see on like multiple choice or something, I would draw it like the following. Right, so I just drew the fused part in like a vertical line, and then so this fused part is carbons 4 and 8. So now 4 is bound to 5, which is bound to 6, bound to 7. 8 is bound to 9, which is bound to 1 and 2 and 3. And 2 and 3 has the double bond, and then 2 and 3 have the methyl groups as well. So that would be the answer. So you'll notice that, I mean, you could have drawn this differently. And again, it takes some practice to do this, but let's just say, I did it like that, right? So 1, 2, 3, 4, 5, 6, 7, 8, and 9. Right? So you'll get to the same thing. You're just going to get this kind of weird intermediate, right? If you draw the arrows and you do the whole thing, you'll get to the same exact step that we were. It's just now your bonds kind of are wonky, something like that. I'm trying to draw it like the way it was drawn here, but all you need to do is count your carbons there. So you'll see, well, I drew one too many here, but you would count, if you kept track of your carbons correctly, you would count that there's 5. So then you just need to draw a pentagon and you can get to your nice structure like the one that I've drawn here. So anyway, hopefully that is clear. Moving on to question number 8 here. All right, so here we have a conjugated diene, and we have a very strong electrophile in the HBr acid. This is going to be an electrophilic addition type of mechanism, but we have 2 potential alkenes, and when you have 2 alkenes, you're just going to do the reaction at both and see what you get. So if we react electrophilic addition at this first alkene, we get this, right? And keep in mind, you're going to form the more stable carbocation, which in this case is the tertiary and allylic position that I've drawn the carbocation at here. And so then the bromine will add there in the next step. And now you're like, well, wait a second. Don't we have resonance? Right? Can't this pi bond move here and create resonance? And yes, it could, but here we have low temperature, so this is a kinetic driver. So the most stable intermediate is this kinetic tertiary intermediate here, so it's going to form the bromine at that position without the rearrangement because we don't have suitable energy. Now, what if the alkene attacks with the other alkene attacks? Well, it can. And when it does, we get this intermediate. And again, we have resonance possible there. But this carbocation is more stable because it's secondary and allylic. If we were to put the carbocation there, it would be just secondary. So this is by far more stable. And what's going to predominate? Then the bromine can add at that position. And that gives us the product. Both of these are racemic, by the way, which means that there's a 50-50 mixture of enantiomers because our intermediate is planar. There's no preference if it comes from the bottom face or the top face, so it will come at both in a 50-50 manner. So we'll get both. And again, the temperature is too low to facilitate a rearrangement, resonance rearrangement. So we get those two products. All right, moving on to the next question. So here we have a alkyl benzene. This is toluene again. This is a very strong oxidant. This is one you kind of have to just be able to recognize and more or less memorize it, I guess. The mechanism is complicated and again, probably not going to be asked, but this is a strong oxidant which converts your methyl group to the fully oxidized version that it can be, which in this case is a carboxylic acid. So that's exactly what it does. This is just straight up oxidation, increasing the oxidation state of the methyl as much as possible. All right, moving on to the last question of this set. So here we have a Friedel-Crafts acylation. So again, the intermediate that's formed here, I'm not going to show the entire mechanism, but it's this one. Right, and then the electrophilic aromatic substitution can occur there, and this will give us the product. Let's draw it here. Doesn't matter. You get to pick where it binds, since it's the first substituent. And then this is a reductant. This is the Wolff-Kishner reduction, but all you need to know about this is it's a strong reductant, which means that we get rid of the ketone and we reduce it all the way to the alkyl group. Right, so you retain your number of carbons, 1, 2, 3 like this, and you get all the way down to the alkyl group. Then this last step here is a NO2 producer. Right, so we're going to add the nitro group to this molecule here. So this is a electron donating, so it's ortho-para directing. So we'll get two products, ortho and para. Here's ortho, and then here is para. And by the way, for synthesis purposes, synthesis questions, we assume that you can separate ortho and para to get your one isolated product. But here, in this type of predict the product question, you should include both because they're both going to form. All right, here we have our next question. So we've already looked at this molecule before. This is phenol. And phenols are very acidic. So they can be removed, that acidic proton can be removed with a base, even as weak as a hydroxide, which isn't a particularly strong base compared to an organolithium or something. But that will get us to this step. Now we've created an excellent nucleophile that can react with our pretty good primary electrophile here, the alkyl halide. So that's what will happen. And this will create an ether. This is an example of the Williamson ether synthesis, which you've probably looked at in first semester organic, but this type of stuff can come up again and again. And here we're taking advantage of the stability of the conjugate base of the phenol to facilitate this type of reaction. So that's the answer there. All right, so here we have our next question, and this entire scheme is called the Wittig reaction. And this creates a alkene in the cis geometry. And we first do this by transforming the alkyl halide to the triphenylphosphine intermediate here. All right, what this does is create these protons become very acidic. So you can remove them with a strong base like butyllithium. And what that does is create the ylide, which is now a carbon nucleophile. And that carbon nucleophile can react with a ketone like we have in this question. Right, so when this happens, you have to keep track of your carbons here. So this is carbon 1 and 2. So what we've done is created a bond between carbon 1 and 2. So this is 1 and here's 2. 2 is bound to the oxygen still, 1 is bound to the triphenylphosphine, and then 2 is bound to an ethyl group and a methyl group. Right, so now the oxygen will attack the phosphorus. We will get this 4-membered ring intermediate, like this. And then let's keep track of all the carbons now. So 1, 2, 3, 4, 5, 6, 7, and 8. And now these 4-membered rings can cleave on themselves. So they will do in this concerted type of mechanism where you form a phosphorus oxygen double bond and the alkene in the cis geometry. So this is going to give us our product here, which forms the alkene with the ethyl group. Here's carbon 7 and 6. This is 5, and this is 4, and then 8 is up here. And then 4 is bound to 3 here, and 2 and 1. So 4 is there, 3 is there, 2 and 1. And then, by the way, we formed this triphenylphosphine oxide here, which you don't really need to know the name of that, but that's just the phosphorus oxygen double bound species. So this is useful because this can stereoselectively make the Z isomer of the alkene. The Wittig reaction gives us a way to make these alkenes from a stabilized diolide and a carbonyl. All right, let's move along. Here we have question number 23. This is a standard Grignard, so CH3 minus is what we're essentially providing to the reaction mixture. Here we have a carbonyl, which can be activated by protonation with this acid catalyst that we have here. Then the Grignard can attack, and this will give us our product. Nothing fancy in this one. We just create the T-butyl alcohol after protonation of the oxygen. All right, moving along. Here we have the same starting material that we had in an earlier question with a strong electrophile. But now we have very high temperature. So we can get the thermodynamic products, which are the ones that form after some resonance intermediate, usually. So let's take a look at the intermediates again. So here is the first intermediate with the proton adding at the top carbon there, exocyclic carbon. And if this rearranges like so, we can then form this intermediate with the bromine adding there. This is thermodynamic, one thermodynamic product, because, by the way, it's racemic, can add to the planar carbocation and either above or below the plane. But the alkene is more substituted than it was here in the kinetic products, making it more stable. Then if you consider the other option, which is if you add this proton at the bottom carbon there, because again, this is secondary and allylic, which is more stable, then you can have this type of resonance, which is, if you notice, gives us a very similar product, a very similar intermediate here. This is allylic, so it's a reasonable primary carbocation because it's allylic. Then the bromine can add to that top carbon. Again, you don't call this racemic because it's achiral. And that would be the two thermodynamic products because that alkene is more substituted as well. So those are the two products when you have very high temperature. All right, and here is the last question of this set. So here we have a Diels-Alder where we're going to make a bicyclic product, which can be very confusing for students. So first, let's arrange these two products or reactants in a way that looks like Diels-Alder. So here we have our diene, and then we have a trans dienophile. Okay, so the stereochemistry of the diene and the dienophile is retained in the Diels-Alder reaction. So we're going to have a trans relationship in the product here. So now we're going to create, again, our 6-membered ring, our cyclohexene, right, like those reaction arrows. And when the substituent is coming on the inside, that is endo. It's an endo approach. And endo approaches are going into the plane. so they're dashes. And going away are exo approaches, and those are wedges. So this intermediate then, or the product I should say, is this cyclohexene with, so let's count our carbons here, keep track of everything. 1, 2, 3, 4, those are these ones. And then we created a bond, so let's call this 6 at the top actually, and 5 down here. This is 5 and 6. And 5 we said is an endo approach, so that's a dash, CHO. And the exo is a wedge, CHO. And then don't forget, we still have a bridge between carbons 1 and 4. So we still have a bridge in this product as well. All right, so this is the correct product with the correct stereochemistry. Now it's just a matter of drawing it like how you're actually going to see it. So just like rearrange arrow. And how you will actually see it is in this like pseudo chair form. Because this shows the relationship of that planar, or that sp3 carbon that's kind of sticking out there. All right, and then we've retained this is 2 and 3, this is 4 and 1, and then that's the one sticking out, and then that makes this 5 and 6. Now, it kind of depends on who's drawing this. I've seen dash and wedge be used here, but since this is like pseudo chair, you can show this is like a pseudo axial position for the CHO, and then like pseudo equatorial here. Again, these are 3-dimensionality, and it's not really a chair. So really what you're showing is this is kind of coming out of the plane, this is going in the plane. So again, that's why maybe dashes and wedges are a bit better there. But the important thing is to show that you have this trans relationship from the endo and exo approach, depending on the substituent that you're looking at. All right, here we have our next set of questions. So again, we've seen this type of reaction situation many times now. This is just a nitrator, adds NO2 to our benzene, an electrophilic aromatic substitution. Now this is extremely electron withdrawing and therefore meta-directing, so our electrophile here is going to add to the meta position. So our product is just the meta nitro and acyl relationship. Again, just count your carbons and make sure you have everything checked, and this would be the product. Okay, let's move on to question number 3. All right, so question 3, we have a nitrogen nucleophile for the first time in these carbonyl species that we've looked at. So nitrogens are extremely nucleophilic. Again, they're larger atoms, so that makes them much more nucleophilic. So they can attack the ketone without any catalyst. Sometimes catalysts are used, but it's not necessary simply because the nitrogen is so electrophilic, or nucleophilic rather. So what you get is this intermediate, and then there's going to be a proton transfer. Again, kind of depends on the solvent, but you can draw this intramolecularly if you want. That's usually acceptable. And you'd get to this intermediate here. And then another proton transfer occurs. Again, this can be done by the solvent. Usually you'll have some base or acid in this to help this along. But this is going to create water and nitrogen minus. And then the lone pair there that has a negative charge can come down and kick out the water. And this will give you the actual product, which is the imine with an I. Okay. When you have a primary amine attacking the carbonyl, you always get an imine product, which is a carbon-nitrogen double bond. All right, moving on to the next question. This is our last predict the product question. So here we have an alkyne, and we need to recall that alkynes, terminal alkynes, have acidic protons. So sodium amide, super strong base, that's going to make the alkyne carbanion. This is now a great nucleophile which can attack our electrophile in the aldehyde there. So that's what's going to happen. This will then make this product. Again, count your carbon. So 1, 2, 3, 4, 5. So here we have 1, 2. That's 1, 2. So this is 1, and then 2, and then 3, and then 4 and 5. Notice that you should have this linear geometry all the way through the alkyne, as I've shown here. I have gone beyond step 3, which protonates the alcohol. But that's the only difference between what I've mechanistically shown and what my structure is. And then Na metal, sodium metal, and NH3, and this acid workup are a trans alkene former. They're a trans reductant. So this final product then is just the trans alkene. So that would be 1, 2, 3, 1, 2, 3 here, like that. 1, 2, 3, 1, 2, 3, 4, and then 3 more carbons. 1, 2, 3. So let's count 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. This is correct, and it's trans, or E, most accurate, is our alkene product because of the sodium metal, and ammonia is the trans former, not the Lindlar's catalyst, which would make the cis, or Z. All right, now we have a couple questions that are synthesis, and then some NMR to finish this out. So 29, we're asked to synthesize the following molecule from acetone and anything else, any other reagent. So if we look at our product here, we can see that we have the acetone moiety where I crossed the alkene. So what this immediately screams to me is it's a Wittig reaction with an acetone, which is that moiety, and then what is on the right of my squiggly line is an alkyl halide. Right, so we have a 1, 2, 3, 4, 5 carbon alkyl halide to start this with, and we can use any other reagents, but like acetone is required, but anything else. So 1, 2, 3, 4, 5. So I just start with a bromopentane here. Then we can do the normal ylide formation stuff. This is going to make, I'm doing this a bit abbreviated since we've already seen this, right? That makes this. This can then react with acetone and give us the product, right? Which is, all right, so 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. That will give it the correct product, which is what we have, what we're asked to make. So the key to that question was recognizing that we're forming an alkene and we had to start with an acetone. So the only way we know how to do that is the Wittig, and then it was a matter of identifying what the Wittig reagent needed to be, and then simply making that, and that would put those two things together, and you get the product. All right, our next synthesis is of a benzene, a nitrobenzene that is ortho. So we have to start with benzene. So we're asked to synthesize the following molecules with starting with benzene. So this has to be electrophilic aromatic substitution. So it's simply a matter of what needs to be added first. So if we added the nitro first, that would put the alkyl group in the meta position. That's not going to happen. That's not what we want to happen. And also it wouldn't happen because nitro groups are so electron withdrawing that Friedel-Crafts alkylation actually doesn't work on them. That's kind of an aside. But the point here, you need to do your Friedel-Crafts alkylation first. So you need your alkyl halide with the aluminum trichloride catalyst. That will give you the ortho, or excuse me, that will give you the toluene. And then you need to do the nitration conditions, which is going to give you the ortho and para products. And as I mentioned earlier, you assume that you can separate out the ortho and para here, so I'm only going to draw the para, but you also make ortho, but just make note that you can separate that, and you'll get, this is the answer. All right, here we are asked to work a couple more synthesis questions and then the NMR. So Here we're asked to synthesize benzene, or from benzene, this molecule. So notice that they're meta, the relationship is meta, I should say. And the way to do that is we need to add a electron withdrawing group to the benzene first. So instead of alkylating, which was possible, what we should do is acylate. Because if you acylate benzene, you'll get an electron withdrawing group that can be reduced to the alkyl group. So this is the first step. Then we can chlorinate, because now it will go in the meta position. Right? Because this is electron withdrawing, ring deactivating, and therefore meta directing. So we'll get to this intermediate, and then we simply need to reduce this to the alkyl group, which can be done many ways. I commonly have the Clemmensen reduction memorized, which is zinc mercury catalyst with acid and some temperature. Will reduce the acyl group to the alkyl group. And by the way, I might spell this wrong, but it's the Clemmensen reduction was that last step. So check that out. That is these conditions here. So it's all, for these electrophilic aromatic substitution ones, it's all a matter of the order that you add and remove groups. All right, and we'll move to the last synthesis question here. So again, we're starting with benzene, so electrophilic aromatic substitution, but it's just a matter of the order. So here we have a para-acyl group. So again, we know that we need to acylate, but we need to then make it such that we can add the second acyl group in the ortho position. So to do that, you need to acylate first, then reduce the acyl group to a alkyl group, which is ortho-para directing, then acylate again, and then transform the alkyl group back to the acyl group, which can be done with an oxidation step. So that was a lot to digest, but what you need to notice is, again, you just start with your acylation. And now we want to add para, so we need to reduce this. So again, we just use our Clemmensen reduction. Or, you know, there are other ways to reduce this, but this is one. Then we acylate again. And now I'm only going to draw the para, but again, you get ortho and para, and you'll just have to make note that you can separate out the ortho from the para. But now you just oxidize the alkyl group. So you can use like CrO3 and sulfuric acid and water or something, so, aqueous sulfuric acid. This will protonate. Not protonate, it will oxidize the alkyl group back to the ketone, and that gives us the product. There's a lot of things you can do here, but what you need is an oxidant, a strong oxidant, but not too strong to oxidize all the way to the carboxylic acid. Like potassium permanganate, KMNO4, would be far too strong to just give you the ketone. So you got to be careful with that. But chromic, this chromate, chromic acid, stuff like that would be fine. It would only make the ketone. All right, and next we are going to work two NMR questions, and that will conclude this video. So here, question 33 is propose the structure of an unknown ketone with the molecular formula C4H8O. So again, we should start with the degrees of unsaturation. If you're not familiar with this, again, I'll have another video in the description that explains the degrees of unsaturation, but it's the number of hydrogens that are, if the molecule was saturated, minus how many are actually there, then minus halogens, and add nitrogens if any are present. But so here, this would be 4 times 2, which is 8, plus 2 is 10. So 10 hydrogens if it were saturated, minus 8, that's how many are actually there, 10 minus 8 is 2, divided by 2 is 1. So we have 1 pi bond or 1 ring. All right, so, and we know we have a ketone, so this pi bond is probably the ketone, or the degree of unsaturation is probably the ketone. All right, now let's look at our peaks here. So about 1, we have a 3 hydrogen triplet, so that's probably a methyl group that's bound to a CH2, because these 2 hydrogens will give yield to the triplet there. Then if we look at the next peak, this is a CH3 that's a singlet, and it's around 2. So it's a methyl group probably bound to the ketone. That's what's going to give it the 2 chemical shift and the singlet pattern. Then if we look at this 2 hydrogen, this is a quartet. So this is a CH2 bound to a CH3 and bound to the carbonyl because it is around 2.5. So when you consider all of those options, this has to be 2-butanone. This has to be the following structure here, because here, let's call this A. This is our methyl group around 1. B here, this is our CH2, that's around 2.5. And then C, here is our singlet, 3 hydrogen singlet. All right, here is the last question for this video. So again, it's NMR, and we're asked to determine the structure of the unknown ketone with molecular formula C6H8O2. And again, it's a ketone, at least 1 ketone in there, so we have to have that type of structure. Again, you should start with the degree of unsaturation, so that's 1/2 the number of hydrogens if saturated, so that's 6 times 2 is 12, plus 2 is 14, minus 8, there's no halogens or nitrogen, so 14 minus 8 is 6, divided by 2 is 3. So we have a lot of possibilities here. We have 3 pi bonds, 2 pi bonds in a ring, 1 pi bond in 2 rings, or 3 rings. So 3 rings is pretty unlikely. Even 1 pi bond and 2 rings is unlikely. It's probably 2 pi bonds in 1 ring, but we'll check. So here, since there's only 1 peak and there's 8 hydrogens all at the same peak, this is heavily symmetric, right? So how can we make it such that we have 4 CH2 groups that are exactly the same when we have 6 carbons? So it has to be a ring with all 6 carbons, because that is conducive for having CH2 groups that are symmetric. Now, they need to be perfectly symmetric, so that means the ketone groups that we have need to be in this pseudo-para. They need to be across from each other. We know that for 2 reasons. 1, the symmetry that I've stressed. 2, if we look at the chemical shift of these CH2 groups, they're almost at 3, which means that these CH2 groups are bound to oxygens, or excuse me, are bound to carbonyls, I should say, like that. And additionally, it's a singlet. So again, it means that not only is it heavily symmetric, the CH2 groups are identical, because identical groups don't split each other. Remember, if you have like a methyl group, for instance, these hydrogens don't split each other because they're identical. That idea is the same if you have CH2 groups or any type of group that is exactly the same because of symmetry or some other reason. Symmetry is the most common, that will make it such that they don't split each other and you just see singlets. So that is exactly the case here. This is in fact the right answer because this CH2 groups are all identical and they would give rise to this peak. Right, so what I'll show here towards the bottom is all of the possible symmetry. I mean, just a few of them. Like, there's so much symmetry in this molecule that's why all the CH2s are exactly the same. So the most obvious is that you have the symmetry across the alkene, or across the entire cyclohexane where the carbonyls are, but you also have symmetry this way, and well, that's really all the symmetry that you have, right? I mean, you have rotational symmetry, but yeah, those are the 2 big angles, because vertically they're not symmetric, horizontally they're not symmetric, but at these 2 angles, and then rotationally they're symmetric. So that makes it such that all the CH2s are exactly the same, they don't split each other, and we see the signals at where we see them. So that is all I have for this video. I hope you found it helpful. If you did, please leave a like and subscribe to the channel for more content like this. If you have a topic idea or suggestion, please feel free to leave it down in the comment section below, and I will get back to it as soon as possible. So I'll see you all in the next video, and I hope you have a great day.